Hello everyone, and welcome to mini lecture 3, Introducing Inferential Statistics in Research. So in the previous mini lecture, we looked at some of the key concepts, such as populations and samples, and how we can use mainly descriptive statistics to help us summarize data using measures of central tendency and variability. We introduced the idea of the standard normal distribution and also probability and statistical significance. So in part 2, what we're going to be doing is building on that, particularly statistical significance, in something called Null Hypothesis Significance Testing framework. We're going to look at the different approaches to statistical testing and how you might choose between those based on the different kind of research scenarios you're presented with, and also look at interpreting statistical tests and how it's not all about statistical significance. And we'll also look at quality appraisal in quantitative research, so trying to think about how we can judge whether the statistics that have come from a piece of research are quality or not. Okay, so to look through the learning outcomes for part 2 then, so by the end of this session you should be able to describe null hypothesis significance testing. You should be able to define key concepts including the p-value, effect sizes, what we mean by research design, and you should be able to identify the parametric data assumptions. You should also be able to identify core inferential statistical techniques that are used for exploring differences between groups or conditions or time points, and for exploring relationships between variables. You should also be able to describe some different approaches to quality assurance in quantitative research, and to be able to articulate the strengths and the limitations of statistics in research. So before we go any further, I think it's helpful to look back at this slide we looked at in part 1, thinking about why we need statistics, what's the point of them. So we've seen that statistics can help us to organise, summarise and simplify our data so we can communicate it to other people. But we have introduced the idea that we can use it to predict the likelihood of events occurring, the likelihood of changes in variables or differences between groups occurring. And we've introduced the idea of using statistics to make inferences or to draw conclusions about a population from which a sample has been drawn. What we're going to be really looking at then in this session is thinking about hypothesis or theory testing and using statistics in empirical research as evidence to support a hypothesis or not. So hopefully by the end of this session we'll also see that statistics can play a role in that evidence-informed decision making, and also we'll look at some of the markers of what quality in quantitative research and how we can use statistics to judge that. But we have to remember all the way through this that our statistics are only as good as our empirical studies are reliable and valid. So it's all based on really the quality of the research and the research design about how much weight we can put on the conclusions we draw from our statistics. So as I've said before, broadly speaking, there are two categories, and we're going to be looking at inferential statistics today. So this is really where we use knowledge about the way data behaves to identify whether values we've observed in a sample are likely to have occurred by chance, or if it suggests something about the relationships between variables or the differences between groups or so on. And the idea is that we can use that, if our research is robust, to make inferences about the parameters in the population. So in part 1 we introduced the idea of probability and statistical significance, and we linked that to the standard normal distribution. So this is what we looked at in part 1. We can see that we have the bell curve, the normal distribution, which is a symmetrical distribution with generally sloping sides. We can see the values in the tails are far less likely to occur by chance, and actually this is where we get the 0.05 cutoff for statistical significance. So we know that within a normal distribution, the vast majority of data points are going to fall within -2 and +2 standard deviations around our mean. So we can use that to draw conclusions. So what I mean by that is, when we're looking at statistical significance, what we're trying to decide is how likely is the finding that we have observed to have occurred by chance? How likely is the finding that we've observed to have occurred if the null hypothesis is true, that there's nothing going on? And so if we have a look at this representation here, what we're saying is that when you get to the tails of a distribution, very unlikely to observe a value that is that extreme. So if you observe a value in the tails of the distribution, we say it's a very low probability of observing that value, then we can reject the null hypothesis, that there is nothing going on. But if we have a very high probability of observing a value, so for example it falls within where the bulk of scores would be expected to fall, then we say that it has a very high probability of being observed, and we have to retain the null hypothesis. So if it's something that we're likely to have observed just by chance, then we have to retain a null hypothesis. If it's very unlikely to have been observed by chance, then we can say that there is something going on and we can reject the null hypothesis. So what we need is a value that will allow us to assess the likelihood of identifying a difference between the means, for example, in this example, that is as or more extreme than the value we have observed. And that statistic is the p-value, the probability level, also called the probability value. And that's essentially what this cutoff is here. So what we would be saying is we've generated a statistic which is based on the difference between these sample means that is so unlikely to have happened if the null hypothesis is correct. It's so unlikely that actually we can reject the null hypothesis and say, no, there is something going on. There is a genuine difference between our groups. So I mentioned there that what we have to do is we have to take our sample means and convert those into a statistic, and then we can look at whether that is unlikely to have happened by chance or not. So essentially we've looked at the normal distribution, but there are lots of other different types of distribution which are all based on statistics. What you would normally do if you're doing this by hand is you would look at your observed value from your data, you'd calculate the statistic, for example, based on the difference between the two samples' means, and you compare that figure, that observed figure, to a table of critical values based on the characteristics of our data, and use that to decide whether we have a statistically significant result or not. Now, don't worry about that too much now. We're going to actually look at some examples of that in a bit. But what we have are lots of different types of distribution of statistics. So this is something called a distribution, an F distribution. This is a distribution, a T distribution, and this is something we're going to look at in a bit. This is a chi-square distribution. So there are all sorts of different statistics that you can draw on, and choosing between them will depend on what your data looks like. So we'll actually be looking at that in a little bit as well. But you've got lots of tools in your toolbox that you can use if you're doing statistical analysis, and one of the skills is to choose between them. We're actually going to be looking at the T distribution in a little bit more detail later on, and it's very similar actually to a normal distribution, but there are some key differences, and we'll talk through that later. So the p-value helps us to determine whether our results are statistically significant or not. The p-value is the probability of obtaining the observed sample results when the null hypothesis is true. And quite often what we say is, how likely are our observed results if the null hypothesis was true, that there was nothing going on. Now, in different fields, the threshold at which we identify something as statistically significant or not can differ. Now in the social sciences and in a lot of health sciences, we tend to choose a cutoff of 0.05. So the p-value, we would say if something is 0.05 or less than, that's what the symbol means, 0.05, then we can reject a null hypothesis and we can say that something is statistically significant. But in some other, in some pharmaceutical research and things like that, you might have to have a much lower threshold than that, so 0.001 or so on. But what this means is, if we were doing the same piece of research 100 times, 5 times out of that 100, we would say that something is statistically significant when it really wasn't. So that's a 1 in 20 chance of saying that there's something going on when actually there isn't, and the null hypothesis shouldn't be rejected. So a p-value, which is also sometimes called alpha, we mentioned that in part 1, of 0.05 is usually seen as a suitable and appropriate cutoff of a risk of saying that there is something going on, that there is a statistically significant result, when actually there isn't. But as I said, in some fields, you might have to lower that p-value. So it's 0.01, for example, so only 1 times in 100 you would make the mistake of saying something's going on when there isn't. But unless otherwise stated, usually the p-value is 0.05. So if we're just looking at these p-values, imagine these have been reported, I'd like you to just go through them and decide, based on that cutoff of 0.05, which of those would you class as a statistically significant result, just based on the p-value, and which of those aren't. So I'm going to give you a minute to have a go at that. Pause this video, look at each one and decide whether you would say that that was statistically significant or not, and then we'll look at the answers. Okay, so I'll assume that you've paused the video and had a go, and we'll look at the answers now. So a p-value here of 0.001, that is lower than 0.05, so that is statistically significant. This value here, 0.06, is larger than 0.05, so we would class that as non-significant. Now we say that something is non-significant, we don't say it's insignificant, because those have very different meanings. What we're saying here is we don't have the statistical evidence to say that there's something going on. So we say that this result is non-significant. This result is right on the borderline, but that would be classed as statistically significant. This is a lot less than 0.05, so that is statistically significant. Now this is just over statistical significance. So if we rounded that up, that would be 0.06, so that would be non-significant as well. So I mentioned a few slides ago that there are lots of different distributions of statistics other than the standard normal distribution, and that this reflects the number of different statistical techniques that you can apply to data. Now you might be thinking, well, how on earth would you choose between them, or do you need to? Can you just pick any? And this is where you really need to understand how the research has been conducted and designed. The first thing you need to understand is about the research design. What sorts of things are you looking to test? What are you looking at? And the second thing that you need to look at is whether your data meets something called the parametric assumptions. And we're going to break that down now and look at both of those things. But essentially, an understanding of these two things will help you to identify which kinds of statistical tests you should run in which situations, so that you know you're calculating a probability value that makes sense. So the first thing, and I'm not going to go into too much detail about this because I'm assuming that you've looked at this previously, but what do we mean by research design? So a research design is the framework of methods and procedures that you've adopted to answer your research questions or test your hypotheses. So in relation to doing analysis, we tend to break research designs down into a number of different types. You can have between groups designs, and that's where you have independent groups of participants and you are looking at the differences between them. You have within groups designs, which is when you're looking at all the same individuals, but you're looking at them in different scenarios, different conditions or time points. And you might have a mixed between within groups design. So that's where you've got an element of between groups and within groups, and we'll look at an example in a moment. Another type of design might be something like cross-sectional, or sometimes they're called correlational, and that's often where you're looking at information that's available, that's naturally occurring, that you're not deliberately manipulating. You're not manipulating groups that people are allocated to. You're not manipulating the scenario, the conditions, or so on. You're just looking at what is out there and naturally varying in the world. So as I said, with between groups, this is where we're going to be analysing the differences between independent groups of people. So this is sometimes called independent samples. And it's where people are allocated to, for example, a control group or a treatment group. The within groups design is also sometimes called repeated measures, and that's where we're looking at the same group of people, but we're looking at their scores on something under different conditions or at different time points, so before and after an intervention. So we're looking at perhaps change scores. In a mixed design, as I said, you can have an element of both of those things. So that might be where you've got, you're looking at the differences between a control and a treatment group before and after an intervention, and to see what the impact is. When I talked about kind of correlational cross-sectional designs, that's where we're not really making any manipulations ourselves. Quite often it's where we're using survey methods, it's using questionnaires to look at how different variables covary, which is when they change systematically in relation to each other. So that's another kind of branch of different research designs. Now, which research design we have will affect what type of analysis we're looking to do. So before I go any further, I need to introduce some more terminology. And this is about variables. So I've talked about how you might be looking at the differences between groups of people on a variable, or you might be looking at the differences or the relationships between variables. So let's just take a moment to think, what do I actually mean by variable? So a variable is a characteristic or a value which has some variability, some variance, or it has the potential to change. Now within that we could break down variables into two broad types. We can talk about independent variables, which are also sometimes called predictor variables. And that's a variable that is either manipulated by the researcher, or we're looking at naturally occurring groups, things that we're not directly manipulating, but that naturally vary, which don't depend on any other variable in the research. For example, a naturally varying variable in or naturally occurring groups would be groups based on gender. So we're not directly manipulating gender, but we're looking at the impact that gender has on other variables. So quite often an independent variable is the thing that's directly manipulated by the researcher. It's often denoted by an X, but it can be thought of as the variable that stands alone. It's the thing that isn't influenced by anything else in your research design, or it shouldn't be. A dependent variable is also sometimes called the outcome or the measurement variable. And this is a variable whose value depends on that of another variable in your research. It's often called the measurement variable because we look to see, when we make changes to something else, we look at the measurable impact that change has on that variable. It's often denoted by Y, and so what we're really looking at in a lot of the research is, if we manipulate X, what measurable impact will that have on Y? Again, these sorts of this terminology has an impact on understanding how you choose between different types of statistical test. So very broadly, we tend to be looking at either looking at differences between groups or relationships between variables. Now that's a gross oversimplification, but it is sometimes quite useful to try and think of how you can categorize different statistical approaches. Within that, we have to be mindful of how our data performs, how it behaves. Now in part 1 we looked at the impact of having a normal distribution on how we could predict observed values as behaving within that. So we can use it to decide when a value that we've observed is likely to have occurred by chance or not, or so on. So one of the important things is that data that is normally distributed, you understand how the mean, the median and the mode operate, and that they're essentially identical. When you don't have a normal distribution, you can't make the same assumptions of your data. Now, why have I talked about that? Well, broadly, there are two types of inferential statistic. There are parametric statistics, non-parametric statistics. So parametric statistics make more assumptions about how your data should look and behave. It's typically based on the means. So we have to have a normal distribution so that our mean is a good measure of central tendency to use. So it's a good representation of typical values in our data set. So parametric statistics make a lot of assumptions about how your data looks in order to make accurate predictions. Now, sometimes, as we've already seen, our data doesn't behave in that way. We have positively or negatively skewed variables, for example. And so there are alternative statistics called non-parametric or distribution-free statistics. Now, they tend to be less powerful, which is why you don't just use them by default. But they make fewer requirements of how your data should behave. And one of those is that it doesn't require your data to be normally distributed. So if you have variables that are very skewed, large levels of positive or negative skew, then it's usually safer to use a non-parametric test. So the reason that these tests are more suitable in that situation is that they're typically based on the medians rather than the means as a measure of central tendency. So you can start to see how, when we talked about descriptive statistics as being the foundation to understanding inferential statistics, you can start to see what we meant by that. And so having a good understanding of why means and medians are better measures of central tendency in different situations, that'll help you choose between parametric statistics and non-parametric statistics. And these are all important considerations, and we're going to bring those together in a moment so you can see exactly how all of these sorts of things come together. But parametric statistical tests, as well as the normal distribution, which you can see here, make a number of other assumptions about your data. So one of those is that the outcome variable you're looking at must be interval or ratio level. Now, if you think about it, that makes sense because most of these parametric tests are based on means. So if you've got an ordinal or a nominal variable, an outcome, you can't calculate a mean for that, so instantly you can't use a parametric test. You have to have something called independence of observations, and that means essentially that my score on a variable shouldn't be influencing your score on a variable. Another assumption of parametric tests is about variance. Now, we looked at how we calculate variance in part 1, and it's a very useful concept to understanding inferential statistics. But essentially, if we have a situation where we're looking at the difference in scores between two groups, the variance of the scores of those two groups needs to be roughly the same in a parametric test. So the spread outness of scores for each of the two groups needs to be roughly the same in order for us to use a parametric test. Now, this final assumption here is a bit more tricky to understand, but essentially there has to be a linear relationship between your variables. What does that mean? It essentially means you could fit a straight line to it. If you have an unusual relationship between variables where it's all curved or kind of you've got like an upside down S or something, and that's called a curvy linear relationship, that really wouldn't be appropriate to a lot of the parametric tests that you use. Now, don't worry too much about these, because how you investigate them will differ depending on the different test you're looking at. But if you wanted to understand more about how these parametric assumptions work and how they're tested in different scenarios, I'd really recommend reading Julie Pallant's SPSS Survival Manual. She has a brilliant introduction to lots of the parametric assumptions, and then she'll actually talk about how they're applied in different scenarios in different types of tests. So if you're interested in learning more about that, I'd recommend reading her book. And as I said, that's available as an ebook through the library. So why does it matter? Well, as I've mentioned, if we are using a parametric test, we're assuming that the mean is a good representation of a typical score. We're assuming that we have a normal distribution. So that's what the mean is. It's the centre of our distribution, essentially. Now, if we don't have a normal distribution, our mean doesn't mean that anymore. It's not necessarily a good measure of central tendency. So if we use inferential statistics to base our assessment of probability on that, we've got some flawed logic going on there. This isn't going to be the best measure of central tendency. We should probably be using something like a median instead, and that's what a non-parametric test will tend to do. So if we think back to part 1, and we remember that we had a mean age of 30, a median age of 26, and a modal age of 21, we know that we have positive skew because our mean is higher on the scale than our median and our mode. And so probably the median might be a better measure of central tendency. So because we have a positively skewed variable, we might need to use a non-parametric inferential test. But we're not going to go into that too much detail now. That's just a reminder of what we looked at in part 1. As well as measures of central tendency, obviously if you have a normal distribution, you'd normally use a mean and a standard deviation. If you don't have a normal distribution, then the standard deviation might not be the best measure of variability. So it has a knock-on effect. Okay, so what does that all mean? So I'm going to share this with you. So this is by the University of Sydney, and it's a really useful tool. What we can see are all these different names. So independent t-test, Mann-Whitney test, dependent t-test, regression, MANOVA. All of these are different types of inferential statistical test, and they are best suited to different scenarios. And how you choose between them is by knowing your research design and knowing whether you've met the parametric assumptions for the data or not. And we're going to apply this to choose a type of test in a moment. But what we can see here is there are essentially 7 steps in selecting a statistical test. But what else we can see is when we have met the parametric assumptions, so we've got yes to this, we could do one type of test, in this case an independent t-test, and that is a parametric test. But what we also have, if we don't meet the parametric assumptions, so we have to answer no at this point, there is a non-parametric test equivalent. So the non-parametric equivalent of an independent t-test is something called a Mann-Whitney test. So for a lot of these types of analysis, there's both a parametric and a non-parametric version. There isn't for every type of test, but there is for quite a lot of them. So just to illustrate that, if we're looking at a correlation, so that's how two continuous variables, or potentially ordinal variables, how they relate to each other, we're looking at either the parametric version, which would be a Pearson, so both the variables would have to be interval or ratio level, and both would have to be normally distributed. Or if we've got ordinal variables or non-normal normally distributed variables, we could use the Spearman's correlation test. We've already looked at the independent t-test and the alternative non-parametric Mann-Whitney U-test, but there are others as well, so this just gives you an idea. Matched paired is also called dependent t-test and so on. So there are lots of options out there. So if we look back at our example, so our hypothesis was that there will be a difference in the mean recall scores for 2 groups of participants, a control group and a group who've taken part in the memory training intervention. So what can we tell from that hypothesis? Well, we can tell that we need to compare between 2 groups. And we can also tell that this is a between groups design, because some people will be in a control group and some people are going to be in a memory training group. So our independent variable, the thing that we're manipulating, is whether someone is allocated to the control group or the treatment group, the memory training intervention. Our dependent variable, the thing that we're seeing if there's a measurable impact on, is recall score. So let's have a go at using this statistics flowchart, which was developed by the University of Sydney. We have to start at this point. So how many dependent variables do we have? Well, we have one, which was recall. So we would start here. The next thing we have to think about is what's the type of dependent variable do we have? Is it a continuous score or a categorical? Well, on this example, it's a continuous recall score. So we would follow this branch. How many independent variables do we have? Now we've actually only got one independent variable and it has two levels. So the independent variable, if you remember, was group allocation, whether they're in the control group or the treatment group. So we have one independent variable, which is group allocation. It's categorical because you're in one group or the other. There are two because there's a control group and a treatment group. And there are different people in each one. So you're either going to be in the control group or you're going to be in the intervention group. You won't be in both. So at this point we know we're going to have to do either an independent t-test or a Mann-Whitney test. And we would have to look at whether our data meets the parametric data assumptions. So is it normally distributed, for example, in order to decide between these two things. So if we imagine that we've looked at our data, it is normally distributed, and actually what we found is that group 1, the control group, had a score, and there were 20 people in that group, they had a score of 24 and a standard deviation of 5. So we know that most people are going to score within, or many people are going to score within -1 standard deviation and +1 standard deviation around that. So they're going to score between 19 and 29, around that value of 24. Group 2, our intervention, had a mean of 20, and our group 2 also had 20 individuals in it, and it had a mean score of 20 with a standard deviation of 4. So they scored between the vast majority of people, 68% of people are going to score between 16 and 24. We know we have a mean difference between the groups' means of 4 points on the recall scale. Now we've imagined that we've checked the data and it was all normally distributed, and so we can use a t-test to do that. Now there are lots of different ways of doing this. There are different types of statistical package. But for things like t-tests, there are some very good online t-test calculators, and we can plug our information into that and we can get a result, a probability value. So if I click on this link, it takes us to something called GraphPad, and we can enter our data. Now there are different approaches to doing that. What we have is we know the mean score, our standard deviation, and n, the number of observations we have, so we can enter that. And you see it's changed the table where we enter our data. So what we need to do is for group 1 put in the mean, which was 24, the standard deviation, which was 5, and the n, the number of observations, which was 20. For group 2 we need to put in the mean score, which was 20, the standard deviation, which was 4, and the number of observations, which was 20 again. We need to choose the unpaired t-test, which is the equivalent. This is an independent samples t-test, because we've got people who are different people in each of the groups, so they're unpaired. And then we can click calculate now, and it produces a result. So what we can see is that we have a mean group difference of 4 points, which is what we'd already calculated. We have a t-value, which is our observed t-value of 2.79. And we have a p-value that's calculated from that of 0.008. So if we look back at our slides, imagine that this is our distribution. What we're saying is that these are a distribution of t-values. Now our t-value is greater than 2. This is just an illustration, so this is based on a smaller sample size than ours. But our t-value is greater than 2, so actually it's in the tails of the distribution, and it's to the point of being very unlikely to have observed a t-value of that size or greater if the null hypothesis was correct, that there was nothing going on. So what we can say is, well, there is something going on. And we know that because actually we have a p-value that's calculated exactly of 0.008, which is less than 0.05, which is statistically significant. So we know that there is a statistically significant difference between the means of group 1 and group 2, that is a difference representing 4 points. And actually, if we think back to our hypothesis, we can reject the null hypothesis, but this finding might be in a slightly different direction than we expected, because it would suggest that people who are in the memory training group are significantly worse at recall than people in the control group. So that would be a really interesting finding to unpick. I've just included a link here so you can actually see how this works. So when you have calculated a t-value, what you would normally do is look that up on, this is critical values. And if your value for t is larger than the appropriate critical value, then you can reject the null hypothesis. Now our calculator has done that for us, and it's told us the exact p-value, which is 0.008, so we don't have to do that step. But that's how we had to do it longhand in the past. So we can tell from our results that we have a statistically significant difference between the two groups' means, that we can be fairly sure that that hasn't occurred essentially by chance, that we can reject the null hypothesis with some confidence. What that p-value can't tell us is how accurate an estimate of the mean difference our score, our statistics are of the population mean difference between the groups would be. What we need additional information to be able to do that. And if we look back at the website, we can see that the GraphPad test results have given us something else. They've given us confidence intervals. And we're going to look at those now. So what we have to remember when we're doing analysis is that the p-value is not the whole picture of our results. So it can tell us about the probability level, but we need other information as well. And if we think back to the first part of this introduction to statistics, we talked about how our statistics are things like our sample mean or the mean difference between the groups. Those are statistics, and they are estimates of parameters. So what we tend to use is something called 95% confidence intervals. So they're a way of assessing the accuracy of our estimate of the mean difference. Now they're quite challenging to interpret, and there are a lot of misunderstandings out there about confidence intervals, but they are a useful tool. But in our example, we found that we had a mean difference between the groups, and if you look back at the website where we used GraphPad to calculate the t-test results, alongside the p-value we also had reported a lower bound confidence interval of 1.10 and an upper bound confidence interval of 6.90. So somewhere between 1.10 and 6.90, we're saying that there's the estimate of the population mean, but it's a little bit more complicated than that. So what we tend to say is, if we ran this study multiple times, and we sampled from the same population, 95% of the time, our 95% confidence intervals would contain the population mean difference. So it gives us an idea. If we think it's somewhere between 1.10 to 6.90, it's not definite that it's within that kind of area, but it gives us an idea of how precise our mean difference estimate is. So the smaller these two values, the smaller the gap between these two values, the more precise the estimate, and that we would know that 95% of the time our 95% confidence intervals would contain the true population mean difference. So they're a measure of precision that journals are increasingly requesting you report as part of your results. But again, we know that the p-value is not the whole picture, and so we can complement that with information about the precision of our estimates. But there's also something else in terms of the interpretation of results. So just because something is statistically significant doesn't mean that it is clinically significant or it's practically useful. So what we also need to do alongside a p-value is to calculate and interpret something called an effect size, which is a measure of the magnitude or the size of the effect. So the size of the difference between the groups or conditions, or the strength of the relationship between variables. So effect sizes provide a system for telling us how large the effects we've seen in our data really are. There are criteria that you can measure against to see if you found something that's a very small, probably inconsistent level, moderate level, or perhaps very large and very consistent relationship. So the effect size is something that's very useful, and again, this is something else that a lot of journals are now requiring authors to publish alongside their statistical results. There are lots of different types of effect size. So there are things like Pearson's R, so that tends to be used more when you're looking at correlations. So that's where variables vary together in a meaningful way. You have things like eta squared or partial eta squared. Those sorts of things tend to be used with things like ANOVAs, which are where you're looking at the differences between 3 or more groups of participants, or 3 or more conditions, or things like that. And you have things like Cohen's d. So a lot of the rules of thumb for interpreting effect sizes, so small, medium and large, tends to have been developed from the work of Cohen. So if you look on the library ebook search box, you'll find one of Cohen's books about effect sizes and power in statistical analysis. I think it's the 1988 version, and he talks through what these mean, and a lot of the rules of thumb that are presented here are from that work. So, for example, if we wanted to look at whether the difference between two groups' means was small, medium or large, then we would probably use Cohen's d, which is this one, and so on. So we can see that a small sized effect would be something that we would calculate at 0.2 to 0.49. A medium sized effect would be 0.5 to 0.79, and a large sized effect would be 0.8 and over. So we're just going to have a look at that. So we've thought about, we've been using a t-test to compare the means of our two groups, which were the control group and a memory training intervention. And we used a t-test to do that. So we want to produce a measure of effect to tell us how large the difference we identified, which was 4 points. How practically large is that? How useful is that finding? So how it does that is it looks at the means of the two groups. It's divided by what we call the pooled standard deviation. So pooled is just the kind of the standard deviation of the two groups. And to actually calculate SD pooled, standard deviation pooled, we have to take the square root of the standard deviation squared for group 1 plus the standard deviation squared for group 2 and divide it by 2. So we have to do that step first, and then we can plug in the other values into that formula. So if we remember that group 1 had a mean score of 24 with a standard deviation of 5, and group 2 had a mean score of 20 with a standard deviation of 4, we can, first of all, we can calculate our standard deviation pooled value. So that's 5 squared plus 4 squared divided by 2 and the square root of that. So that's 4.53. And then we can take the mean of our group minus the other mean, divide it by 4.53, and we get a value for D of 0.88. So there are lots of effect size calculators out there on the web, so you don't have to remember this formula, but I think it's helpful to know how it's calculated, and Cohen's D for t-tests is something that's fairly straightforward to do. But there are lots of calculators, as we saw for t-tests, there are lots of calculators for different types of effect size as well. But if we look back at our rule of thumb, what we can see is that we would have, based on this, a large effect size. So we now know that we have a statistically significant difference between the groups, that the mean difference we observed was 4 points. We know the precision with which that's estimated because of our confidence intervals, so we know the range within which the population mean difference would fall. And now we know that that represents a large sized effect. So that means that the finding we have is likely to be observable from descriptive statistics, which it is, and it's likely to be consistent as well. So we've had a bit of a whistle-stop tour of all the sorts of things, as well as a p-value, that you need to think about when you're looking at inferential statistics. But it really goes beyond that as well. And one of the things that is really important to remember is that just because something is published doesn't mean that it's good quality. So whenever you're reading any research using statistics or for qualitative research as well, you need to be thinking about the quality of that. So you need to approach it with a critical eye. And one of the things that I find is quite helpful to sort of structure that are using reporting guidelines and checklists to think about how good a piece of work is. So I've just provided 2 different websites that have a collection of different checklists, so I'll take you through those now. So this is called the Equator Network, and one of its aims is to kind of enhance quality and the transparency of reporting in research. Now, there are lots of different checklists, and there's an overview of some of them that are based on different types of research design. So if you're looking at an observational study, you could use the Strobe checklist. If you're using randomized controlled trials, you can look at Consort and so on. But if we have a look at, say, the randomized controlled trial, you will have some information about the checklist, where it was developed. There's a Word version. So what this is looking at is, for a randomized controlled trial, all the different things that are markers of good quality. So what were the specific objectives and hypotheses? Were they stated clearly? It's thinking about things like the eligibility criteria. Were the eligibility, the inclusion-exclusion criteria clear? Did they make sense as well? So there's lots of things that you need to think about across the whole piece of research in terms of its rationale, how it's specified, its hypotheses, whether the data it's collected will allow you really to test those hypotheses and so on. The other link I provided is to the Joanna Briggs Institute. Again, so these are by the Joanna Briggs Institute, and these have some validity information in terms of how they've been applied. And again, you've got checklists for all sorts of different types of study. So, for example, you've got a checklist for quasi-experimental studies, so non-randomized experimental studies. So you've got a PDF or a Word document. And these are traditionally used for systematic reviews to judge the quality of research, but I think it can be really, if you find a piece of research that's really important, that's really useful, it can be helpful to apply these for your own peace of mind, really. If you're looking at evidence-informed decision making, it can be a useful tool to go through. So there's some background to the tool and some explanation of what each of the items on the checklist means and how you need to apply it. And you can go through and get a sense of, was there a control group? Were the appropriate statistical analysis used for the data? What about the reliability of the way the outcomes were measured? Things like that. So those all feed into the confidence you can have in the conclusions of the piece of research, the conclusions drawn from the statistical analysis that they performed and so on. It's important also to think about who is doing the research. Does that party have a vested interest in some way? So again, a lot of journals are now requiring people who are reviewing research or who are publishing research, they have to clarify whether they have any potential conflicts of interest. So it's thinking about who's producing the research and the potential agenda they may have. So thinking just very briefly about the strengths and limitations then of statistics. Some of the strengths of statistics are that they can help you identify consistent patterns in data. So they can be very useful in terms of looking at broad patterns, identifying where variables seem to vary systematically together. They can give you sort of the big picture then. If the research is done well, it can provide a means for you to generalise beyond your observed data from your sample back to the population that sample was drawn from, so you can think bigger again. What you have to be careful of with statistics, though, are where people are trying to say that a hypothesis has been proved with the statistics. We don't prove a hypothesis, but we can use statistics to provide support for it. If that's what they reflect. One of the limitations of statistics is that they can be applied inappropriately, and people can draw conclusions that go beyond what the statistics can actually tell them, so you have to be careful with that. One of the other issues is that there's a perception that sometimes statistics or statistical analysis can fix poor research design. Now, to some extent, they can control for some things that you can't control for research design, but there is no substitute for a good research design, and if the research design is poor, it will have an impact on the conclusions that can be drawn for any statistics, so it's always worth remembering that. And the final thing is the tendency for correlation, which is where we see patterns in data so that there's a systematic varying of scores, say, on one variable, and that's mirrored in some way by scores on another variable, so a correlation. People use that to infer causation, so that X causes Y. But actually all we can say with statistics is really that there seems to be a meaningful pattern between the two. And we can use theory to try and infer causation, but statistics can't prove it, if that makes sense. And a final issue, and you'll see this actually if you read research about mixed methods research, which is where you combine quantitative with qualitative and so on, that quite often statistics can give you the bigger picture in some respects, but what they can't tell you are necessarily the lived experience that people have. So I think there's always an element that they can answer certain types of research question, but not all of them, and so there's also no substitute for qualitative research to answer some types of research question about experiences and the meanings that people attach to experiences and so on. So just to revisit the learning outcomes, it's very much been a whistle-stop tour, but hopefully you should be able to describe what the Null Hypothesis Significance Testing framework kind of is. You should have an idea now of what p-values are, what effect sizes are, what research design refers to, and what parametric data assumptions are. You should have an idea of the different inferential statistical techniques you can use to explore differences between groups or time points, as well as relationships between variables. And you should be aware of tools that are out there to help you think about quality assurance or quality appraisal in quantitative research. Things like the Equator Network with all of the checklists and things. And you should have some idea of the strengths and the limitations of statistics and research, although there are lots of others that we haven't had a chance to look at today. So in terms of some suggested resources, obviously once you have your university login details, there are lots of different very useful books in the Hive, and some of those are also available as ebooks. But in the meanwhile, I'd suggest having a look at some of the sorts of interesting blogs that are out there, including Statistics How To, and also Daniela Navarro's work. She has a number of free online textbooks which look at a range of different types of statistical software, so it's worth having a look at that. There's also some useful outward facing free parts to layered statistics, although you can access more thorough guidelines, you have to pay for those. And there's a link here to Eugene O'Loughlin's YouTube page, where he takes you through calculating some of the different inferential statistical procedures that we've mentioned by hand. So if that's how you prefer to learn, then I'd recommend having a look at his channel. But other than that, this mini lecture's finished. Please do complete the very quick 5 multiple choice question quiz, and that will reveal the final very brief mini lecture on introducing SPSS, and that will be the completion of this part of the module. Okay, thank you.